Okay, I got this problem we have here today from a video from SyberMath. We've got the sum of I plus I squared over 2 plus I cubed over 3 plus I to the 4th over 4, etc. on and on to infinity. Okay, I thought this was a really interesting problem. I want to do this one two different ways. The first one is going to be a lot like what he did in the video, and the second one's going to be something a little different. So the first thing I want to do is just put this into sum notation, where we just notice if I write this, I can write this as like a 1 and a 1 exponent here. And then what we notice is that in every case, we've got the same thing in the denominator as the coefficient. So I can write this as I to the n over n. And we're just summing from 1 to infinity. But then to start with it, what I want to do is just notice the similarity to the power series for natural log of 1 minus x. That power series is just going to be the sum from n equals 1 to infinity of x to the n over n, but there is a minus sign out in front, and actually to make this work a little better, let's just multiply by minus 1 and bring it to the left side of the equation. But then notice what we have right here is exactly like what we have here, just with our x value being equal to I. So what I can do is let's take that value for x and just plug it into this thing. And so that's going to allow me, to express this sum as minus natural log 1 minus I. But then maybe let's just bring the minus 1 into the exponent and rearrange it with log properties, so I can write this as natural log of just 1 over 1 minus I. And then to simplify it, let's just get we want to get the I out of the denominator, so I can multiply by the conjugate on this. So I'll multiply by 1 plus I over 1 plus I. Multiply that out, you're going to get natural log. The numerator is just 1 plus I. When you do this part, multiplying all this out, distributing it out, you've got like a difference of 2 squares. You're going to have 1 squared minus I squared, but I squared is minus 1, so you end up with 1 minus minus 1, or just 2. And so let's just write this a little bit differently. I'm going to just distribute the 2 into it, and I can write it as natural log 1/2 plus 1/2 I. Just doing that to get this into our a plus bi notation. And now technically we could just leave it this way, but I think it'd be a little nicer if we got this into polar form. So let's do that. Let's take our a plus bi and convert this into polar form. And we have our formulas to do this over here to the left. And what we're trying to simplify, we're just focusing on, I don't care about the natural log right now. We're just looking at 1/2 plus 1/2 I. So our a value is going to be 1/2. Our b value is going to be 1/2. So first, in order to get this r value, what I'm going to do is let's just plug into this. So for the r value, we're going to have square root. A squared is going to be 1 over 4, and b squared, same thing, 1 over 4. Putting this together, we have the square root of 1/2. I can just write this as 1 square root of 2. Then next for our theta value, when we plug this in, one thing to think about on this is the sign in front of each of these in order to determine the quadrant, but both these are positive, so this is all going to be in the first quadrant. So what we're left with here is going to be 1/2 over 1/2, but this is just going to be arctan of 1, and for that value we've just got pi over 4. So then we've got our r value, we've got our theta value, we go back to our formula for a plus bi. What's going to happen is we have 1 over square root of 2 e to the theta of I. So let's just take this value, plug it into the natural log, and then see if we can simplify it a little bit more. So now with this, what I can do with log properties is break this up. We've got multiplication here, so I can turn that into addition and write this as natural log 1 over square root of 2 plus natural log e I pi over 4. More log properties, I can bring the exponent out front here like this. And I think I'll actually kind of reverse this. So we'll have I pi over 4, natural log of e. Here we can flip this and bring a minus sign out front. Also on the square root, we can bring that out as a 1/2. So I can have this as minus 1/2 natural log of 2. You could express this a few different ways, but I just kind of like it this way. But here, natural log of e is just 1. And so putting this together, for my final solution, we just have I pi over 4 minus 1/2 ln 2. And that's going to be method number 1. Okay, now for method number 2, what I want to use is looking at the numerators here. Just notice that our different values of I are going to repeat. So like, let's see how this goes. If we look at just I to the 1, of course, this is just I. For I squared, multiply by I on this, and you get minus 1. I cubed, multiply by I again, you get minus I. Do it again for I to the 4th. I times I is minus 1 times a minus sign is just 1. Do it again for I to the 5th, and now you just get back to I. So what's going to happen is it's just going to repeat, and you're just going to get this sequence over and over again. So what that's going to allow me to do is rewrite our series with just different values in the numerator. I mean, I guess some of the values are going to be the same, like I is just I, but we can use this to rewrite each of these terms. So doing it this way, we're only going to have 4 different values in the numerator, and it's just going to repeat over and over again. And from here, what I want to do is split up the real part from the imaginary part. So doing this, we want all the real terms. So we're going to end up with minus 1/2 plus 1/4 minus 1/6 plus 1/8. And then here we'll have all of our imaginary terms. We'll just have that as 1 over 1 minus 1 over 3. Notice that all the even terms end up in the real part and all the odd terms end up in the imaginary part. But now in the real part, what I want to do is let's factor out minus 1/2. So then this is going to become just 1 minus 1/2 plus 1/3 minus 1/4, etc. But now from here, we can look at a couple of common series for this. This first one for our real part, once we have the minus 1/2 factored out, this right here is exactly the alternating harmonic series. Well-known value for this is going to be just ln2. So all this chunk right here is just ln2. Then for the imaginary part over here, we notice the similarity to our power series for arctan, where we've got all odd denominators, alternating sign. The thing about this x part here, if we just look at arctan at 1, then what's going to happen is that part goes away. And so for arctan of 1, if you expand it out, you get exactly this right here. But arctan of 1, we know the value of that is just pi over 4. So for this chunk right here, we'll call this pi over 4. So now that we've evaluated everything over here, let's get rid of this stuff over here. And so putting this together, we have minus 1/2 ln2 plus pi over 4i. And so for the second method, we get the same thing we got in the first method. I don't know why I wrote it in a different order. I think it's probably nicer to have it in this a plus bi notation, but this is the same as this. Okay, there you go. Interesting problem. Good video from SyberMath. I'll give you a link to that one if you want to check it out. Thanks everyone for watching. Have a good day.